Imagine a clear summer morning in the remote Siberian wilderness. Suddenly, without warning, the sky erupts in a blinding flash, followed by an earth-shattering roar. This wasn't a dream, but the chilling reality for witnesses on June 30, 1908, near the Podkamenia Tunguska River. This day marked an event so powerful, so enigmatic, that it continues to baffle scientists over a century later. What unleashed such colossal destruction in one of the most isolated places on Earth? This is the story of the Tunguska Event, one of history's greatest unexplained explosions. The Tunguska Event was an explosion of truly colossal proportions. Scientists estimate its energy yield at an astonishing 10 to 15 megatons of TNT. To put that into perspective, the atomic bomb dropped on Hiroshima was approximately 15 kilotons. This means the Tunguska blast was roughly 700 to 1,000 times more powerful. The seismic waves, or ground vibrations, were recorded globally, traveling across continents. Atmospheric pressure waves, which are essentially sound waves too low for human hearing, were detected by sensitive instruments called barographs as far away as the United Kingdom. It was truly an event that resonated across the entire planet. The effects of the Tunguska event extended far beyond the immediate blast zone. For several days and nights following the explosion, the skies across Europe glowed with an eerie, unearthly light. Observers in cities like London and Berlin reported that it was bright enough to read newspapers outdoors at midnight. This phenomenon, often referred to as bright nights, was a direct atmospheric consequence of the Tunguska blast. It hinted that something extraordinary had happened in Earth's upper atmosphere, scattering light in a way that defied normal meteorological conditions and adding another layer of mystery to the event. The most striking evidence of the Tunguska event's immense power lay in the physical destruction it wrought. An area spanning approximately 2,150 square kilometers, or about 830 square miles, was utterly devastated. To visualize this, imagine an area roughly the size of a major modern city, like New York City, completely flattened. An estimated 80 million trees were blown down, stripped of their branches, and laid out in a radial pattern, meaning they fell outward from a central point, like spokes on a gigantic wheel. This pattern of destruction provided crucial clues about the nature of the explosion. Closer to the blast's epicenter, the destruction took on an even stranger characteristic. While trees in the outer regions were knocked down radially, those directly at the center of the event stood upright. However, they were completely stripped of their branches and bark, resembling telephone poles, and their tops were severely charred. This bizarre pattern suggested an incredibly powerful downward force, followed by intense heat, yet without the direct ground impact typically associated with such immense energy. It was a puzzle that would challenge conventional explanations for decades. Perhaps the most perplexing aspect of the Tunguska event, and indeed the central mystery that drives scientific inquiry, is the complete absence of an impact crater. When an object from space, like a meteorite, strikes the Earth, it typically leaves a distinct, bowl-shaped depression. Given the sheer scale of the Tunguska explosion, one would expect a crater of immense proportions, possibly kilometers wide. Yet, despite extensive searches, no such crater was ever found. This crucial detail immediately ruled out many conventional explanations and forced scientists to consider entirely new possibilities for what happened in Siberia. Despite the magnitude of the event, the scientific world was slow to respond. The Tunguska region in Siberia was, and still largely is, incredibly remote, with challenging terrain and extremely harsh weather conditions. Furthermore, Russia itself was plunged into a period of intense political instability, undergoing World War I, followed by the Russian Revolution and subsequent civil war. These monumental geopolitical events meant that scientific exploration was not a priority. It would be more than a decade before the first serious investigations could even begin, leaving the site undisturbed and allowing nature to slowly reclaim some of the evidence. The first systematic scientific investigation into the Tunguska event didn't begin until 1921, led by the Russian mineralogist Leonid Kulik. Driven by a fascination with meteorites, Kulik was convinced that the Tunguska explosion was caused by a large meteorite impact. He spent nearly 2 decades, from 1921 to 1939, organizing multiple expeditions into the treacherous Siberian taiga. His unwavering determination in the face of incredible logistical challenges and personal hardship cemented his place in the history of this mystery, laying the groundwork for all future research. His initial goal was simple: find the meteorite fragments and, of course, the crater. Kulik's expeditions faced monumental difficulties. The dense, swampy forests, infested with mosquitoes, made travel excruciatingly slow. Despite these obstacles, he and his team eventually reached the epicenter of the blast. They meticulously searched for fragments of a meteorite, digging trenches and sifting through soil, expecting to find the metallic remnants of the celestial body that caused such devastation. However, their efforts yielded no large pieces of extraterrestrial material. The ground, surprisingly, contained only normal soil and vegetation, intensifying the mystery rather than resolving it. While Kulik failed to find a crater or meteorite fragments, his expeditions were far from unsuccessful. He was the first to accurately map the vast area of flattened trees, confirming the radial pattern of destruction originating from a central point. He also observed the distinctive upright, stripped, and charred trees at the epicenter. These meticulous observations provided critical data, establishing the unique characteristics of the Tunguska event. Kulik's work laid the essential foundation for all subsequent scientific understanding, even if the primary goal of finding a meteorite proved elusive, hinting at a more complex phenomenon. With no crater, no large meteorite fragments, and a blast force far exceeding any conventional explosion, the Tunguska event presented a unique cosmic puzzle. For decades, scientists grappled with explanations. What kind of object could enter Earth's atmosphere, unleash such devastation, and then seemingly vanish without a trace? The evidence pointed away from a typical meteorite impact, suggesting something far more extraordinary had occurred. The absence of a physical impact site, combined with the widespread atmospheric effects, became the defining characteristics that guided future scientific theories. The leading scientific explanation for the Tunguska event today is the airburst hypothesis. This theory suggests that instead of striking the ground, the cosmic object exploded high above the Earth's surface. Imagine dropping a very heavy, fragile object from a great height. It might break apart before it ever hits the ground. Similarly, an airburst occurs when an extraterrestrial object, like an asteroid or a comet, encounters significant atmospheric resistance as it plunges towards Earth. The immense pressure and friction cause it to heat up, fragment, and violently explode meters or kilometers above the surface. One of the two primary contenders for the Tunguska culprit is a stony asteroid. An asteroid is a rocky, airless body that orbits the Sun, typically smaller than a planet. Scientists propose that a stony asteroid, estimated to be between 60 and 190 meters in diameter, entered Earth's atmosphere at a high speed. As it descended, the tremendous atmospheric pressure compressed the air in front of it and heated the asteroid rapidly. Because asteroids are relatively dense, they can withstand this pressure for a time, but eventually, the internal stresses become too great, leading to a catastrophic mid-air explosion. An asteroid airburst explains the Tunguska destruction remarkably well. The explosion, occurring at an altitude of approximately 5 to 10 kilometers, or 3 to 6 miles, would generate a massive shockwave that travels downward and outward. This colossal shockwave would flatten trees radially, just as observed. The intense heat from the plasma fireball created by the explosion would explain the scorched, branchless trees at the epicenter. Crucially, because the object disintegrated in the air, its energy was dissipated before it reached the ground, leaving no impact crater and vaporizing any solid fragments into dust, solving the mystery of the missing meteorite pieces. The second leading theory points to a comet airburst. A comet is a celestial body composed primarily of ice, dust, and rocky particles, often described as a dirty snowball. Scientists suggest a comet, perhaps around 60 meters in diameter, was the culprit. Unlike dense asteroids, comets are much more fragile. As a comet hurtles into Earth's atmosphere, the friction and pressure cause it to heat up and sublimate, turning directly from ice into gas, rapidly. This inherent fragility means a comet would likely disintegrate and explode even more readily than an asteroid at a similar altitude. The comet airburst theory offers a particularly compelling explanation for the widespread bright nights observed across Europe. As a comet made of ice and dust vaporizes high in the atmosphere, it would release a massive amount of fine particles and water vapor into the upper layers. These particles, lofted to great heights, could then scatter sunlight effectively, even after sunset. This scattering effect would cause the prolonged atmospheric glow, much like very high clouds can reflect sunlight long after the sun has set below the horizon, illuminating the night sky for days, a phenomenon an asteroid might not explain as readily. Both the asteroid and comet airburst theories are highly plausible and effectively explain most of the observed phenomena: the immense blast, the radial felling of trees, the scorched epicenter, and crucially, the lack of an impact crater and large fragments. The choice between them often comes down to subtleties. An asteroid might better explain the extreme energy release, while a comet provides a more direct explanation for the bright nights due to its icy composition. Ongoing research analyzes trace elements in peat bogs and tree rings at the site for definitive chemical signatures, but both remain strong contenders. Over the years, various other hypotheses have been proposed for the Tunguska event, though most lack scientific support. Ideas such as a mini black hole passing through Earth, or an alien spacecraft explosion, while captivating to the imagination, have no credible evidence to back them up. Similarly, terrestrial explanations like volcanic activity or gas explosions have been definitively ruled out by geological surveys, which show no corresponding seismic or magmatic activity. The scientific community has largely converged on the airburst scenarios because they align with all available evidence, leaving little room for more fantastical explanations. The Tunguska event serves as a powerful reminder of our planet's vulnerability to cosmic impacts. Had the explosion occurred over a densely populated area, the consequences would have been catastrophic, potentially killing millions. This event, along with the more recent Chelyabinsk meteor airburst in 2013, has significantly raised awareness about the importance of planetary defense, the study and development of methods to detect, track, and mitigate potential threats from near-Earth objects. Tunguska taught us that even objects that don't directly hit the ground can cause immense destruction, reinforcing the need for constant vigilance. More than a century has passed since that fateful morning in Siberia. While scientific theories have provided compelling explanations for the Tunguska event, the exact nature of the object, whether a stony asteroid or an icy comet, remains a subject of active debate and ongoing research. The Tunguska event stands as a monumental case study in how nature's most dramatic phenomena can unfold in unexpected ways. It reminds us that even with advanced science, some mysteries retain their allure, continuously pushing the boundaries of our knowledge and inspiring future generations of scientists to look skyward for answers.